will be learning the basics of combinatorics. We will begin from the scratch, but it's the request that whenever we are starting a problem, the students need to pause the video and try solving the problem, because we will solve it immediately. We will not wait. We will not wait. What is the first counting rule? Basically, why we are learning combinatorics, why we are learning these counting rules. Suppose we are given 5 objects, 5 different books, 5 different books, and we have been asked that in how many different ways we can arrange them. I would simply say then we can arrange them in 120 different ways without any calculation, without any practical calculation. I would simply say, because I know the counting principles, because I know the rules. I'm having the rules. Two dice are simultaneously thrown. What are the different arrangement possible? I would just simply say 6 into 6, 36, without practically counting anything. And that's what is the benefit of learning counting rule. That is what is the benefit of learning counting rule. Basically, there are two counting rules: the sum rule and product rule. Sum rule and product rule. What is the sum rule? If an event can occur in n ways or m ways, if an event E can occur in n ways or m ways, then the total number of ways in which the task can be done is n plus m ways, only if the sub events, the event T, we can perform it in two ways, perform it in n ways and m ways, only when these two ways are independent of each other. Independent of each other. That is, sum rule is applicable when the cases, sub cases, are independent of each other. The illustration would make it clear. What do I mean by the word independent? From city A to D, there are two ways to go to city D, either via B or C. There are 9 ways to go via B and 7 ways to go via city C. Find the total number of ways to go to city D from A. Starting from city A, going to city D, through city B, through city C, then two events are independent of each other. Via B we can go in 9 ways and via C we can go in 7 ways. So the total number of ways are 9 plus 7 equals to 16. Because these cases are independent of each other. I am giving an example that when the cases are not independent of each other. In the next page I will give. Whenever the cases are dependent on each other, we will apply at that time product rule. Suppose let us go with the same example. That from city A to city D. But this time the route is like that. First from B to C, then first from A to B, then from B to C, and then from C to D. Here we are having 9 ways, 7 ways, and suppose here we are having 14 ways. Then at this case, the cases are dependent, because first we have to perform these tasks, then only we can perform these tasks, and then only we can perform these tasks. So the entire tasks of the person going from city A to D has been broken down into 3 sub-tasks, 1, 2, 3, which are dependent upon each other. These 3 sub-tasks are dependent upon each other because they are happening in a sequence. And that is the definition of product rule. If a task can be broken down into a sequence of sub-tasks such that each sub-task can be performed in n1 nk ways, definitely the sub-tasks are dependent upon each other because they are in a sequence. First we have to perform the first task, then only we can perform the second task. So they are dependent. Then the total number of ways in which the task can be done is n1 into n2 into n3. Here this is our first question. Here we have to take an assumption. Assume, just wait, that first position is captured by just a minute, question is to be edited. Now it's fine. In how many ways can 3 winning prizes be given to the top 3 players in a game played by 15 players? Assume that one position is captured by only one person. This is not into solver. Yeah, this is because only for explanation purpose. First position, second position, third position. First, second, third. First position can be captured by any of the 15%. Now first position is captured by 1% among the 15%. So we are left with 14% for the second position. Now second of the 14% that were left out, 1% has captured the second position. Then the third position can be captured by 13%. So we can see that the cases are also dependent on each other. So we will just think for their product. That is product rule. Now there is a simple application of product rule which gives us a very important result often used in number theory questions, that find the number of positive factors. Finding the number of positive factors. This is very easy also. To find the number of positive factors of a number n. This is p1 whole to the power a1. Suppose we are taking the case of 75. 75 can be written as 3 whole to the power 5 square. Then how many factors does it have? Let us try to find out the factors manually. 1 into 75, 3 into 25, 5 into 15. So we are getting 6 factors, right? Now in combinatorics, we will not count, sir. What are the possible values this 3 to the power 1 can take? Either 3 to the power 0 or 3 to the power 1. 5 to the power 2 can take 5 to the power 0, 5 to the power 1, 5 squared. So it can take 2 values, it can take 3 values. The number of factors are 2 into 3 equals to 6. Here also we are getting 6 factors by practically finding out all the factors, and by combinatorics we are getting 6 factors. So if we just simplify the case, we can see that p1 whole to the power a1, this a1 can have values ranging from 0, 1, 2 up to a1. Let me write it for I now. So it is having ai plus 1 number of values. Is it clear? Because for the case of 3 whole to the power 1, we have seen it can take 0, 1. And this 1, if you just think, 1 plus 1, same thing. Same thing, yeah. Same thing only. And the cases are also dependent on each other, we have already seen. So the number of factors are a1 plus 1, a2 plus 1, a3 plus 1 up to an plus 1. It should be absolutely clear. Problem solving strategy, we just need to solve the cases. We need to first sort into the cases, sorting into cases, solving the case, identifying the relationship between the cases. That are the 3 problem solving strategy. Now, based on the idea of what we have learned in product rule, we need to solve this problem. This is a very beautiful problem. You can pause the video. I am solving it now. M cube can be written as 20 whole to the power 21 over n square. Also it can be written as 2 whole to the power 42, 5 whole to the power 21 over n square. Now this n square can be written as 2 whole to the power twice a into 2 whole to the power 5 5 whole to the power twice b. That would give us 2 whole to the power 42 minus twice a into 5 whole to the power 21 minus twice b. Now what are the permitted value of b such that we would get a cube? We would get a cube. (42 minus twice a). What are the permitted value? You just see. Here I am writing for the values of a, and here I will write the result. 42 minus twice a equals to 0, 3, 6 up to 21. 8 values we are getting. You just see all of the values. 42 when a is 0, when a is 3, it is 36 up to 0. So 8 different values of a are there. 8 different values of a are there. Similarly, for this we will find 5 whole to the power 21. If you just find it only 21 minus twice of b, and here I am taking the values of b. B equals to 0, then 21, b equals to 3, then 15, b equals to 6. Then here we are getting, these are the permitted values for b, for which this 5 whole to the power 21 minus 2b will give us a cube. So for b we are having 4 values. So the number of ordered pair is just simply 8 multiplied by 4. 8 into 4, 32. This would be the answer. Find the number of ways to place 4 distinct natural numbers in the vertex of a squared table such that the sum of the number is 16 and the sum of the number in each diagonal are equal. Sum of the number diagonally are equal. This diagonal will give us equal number. Suppose the numbers are a, b, c, d. Then a plus c will be 8 because the numbers are equal and the total sum is 16. So what are the different pairs we are having? We are having 1, 7, 2, 6, 3, 5, 4, 5, 6, 7, 1, 2, 3, 4. For b and c also we are having the same result. So we can just ignore the case. The number needs to be distinct and the arrangement will also matter. So if we just choose 1 and 7, the first pair, then this 7 and 1 cannot be chosen again. 7 and 1 cannot be chosen again. It has been already chosen. So we are left with 1, 2, 3, 4, 5 pairs. So for this arrangement, this and this, we can say that 6 into 5 possibility. We have not considered this because here a special case is there. Both the numbers are same, 4 and 4. While considering 4 and 4, if we just take that a and c, this is also 4, this is also 4. How many possibilities we are left with? Here we are left with 1, 2, 3, 4, 5, 6 possibilities. That's why it is different. Plus 6, the case of 4 and 4. So we will get 6 into 6 cases. 36 is the answer. How many 6-digit numbers are there in which no digit is repeated? Even digit appear at even place and odd digit appear at odd places. And the number is divisible by 4. Let's solve it. Let's solve it. Let's solve it. First of all, divisibility rule of 4 says that the last two digits should be divisible by 4. Last two digits should be divisible by 4. Let the 6 numbers, let us write 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is odd position, this is odd position, this is odd position, this is even, this is even, this is even. What are the odd values? Such that the number should be divisible by 4. That we have to keep in mind. We have 1, 3, 5, 7, 9. And even values are only 2 and 6. Because 12 and 16 both divisible by 4. 32, 36 divisible by 4. 52, 56 divisible by 4. 72, 76 divisible by 4. 92, 96 divisible by 4. So here we are having 5 possibilities. And here we are having 2 possibilities. Now one odd number has been already chosen. And it is given that no digit is repeated. So here we are left with 4 odd number and here we are left with 3 odd numbers. For the even number, one odd number has been already chosen. One odd even number has been already chosen in the first case. Here already chosen. So for the even number we are having, one is already chosen. We are having 5 even numbers, 4 and 3. So what we can interestingly see the fact that this is nothing else but 12 square into 10. This is 10, this is 12 square. So the calculation is also easy. 12 square into 10. Answer will be 1440. Very simple. Let us move forward. Yes, answer is 1440. Number of permutation. Number of permutation. Order matters of n things taken r at a time. Number of permutation. What do I mean by the word permutation? Permutation means arrangement. Suppose we are having 5 balls, 5 distinct balls, and we want to make arrangements of 3 balls or permutations of 3 balls. Permutation of 3 balls. So how many different possibilities are we having? For the first case 5 balls only, second case 4, third case 3. This if we just see that this equals to 5 factorial over 5 minus 3 factorial. Now what is factorial? This is factorial. Factorial means the product of, n factorial means the product of all natural number less than or equal to 5. Product of all natural number less than or equal to 5. So 5 factorial is 1 into 2 into 3 into 4 into 5. Likewise 4 factorial will be 1 into 2 into 3 into 4 equals to 24. Another important thing to note is n factorial equals to n into n minus 1 factorial. That is 5 factorial can also be written as 5 into 4 into 3 into 2 into 1. Now this part is what? 4 factorial. So 5 into 4 factorial. That is n into n minus 1 factorial. N factorial. So this is what factorial is. Factorial means. So I hope this is clear. How does this formula comes? Here only we have shown the formula here in terms of n. Let's suppose we are having n balls. This is the case. N balls small r box. Number of ways in which the first box can be filled is n. Number of ways the second ball can be filled is n minus 1. So on, the rth box can be filled in n minus r minus 1. This is equals to n factorial over n minus r factorial. That's what the formula of permutation is. Combination means what? Combination means choosing, grouping, we can say. That we are having 5 balls. Five different balls. In how many ways? We can put 2 balls in a box such that their arrangement does not matter, regardless of the arrangement, regardless of order of the balls, regardless of the order. At that case, we will use this formula 5 choose 2. Now, if order matters, what will happen? Just see. If order matters, this is same as arrangement only. So we have the formula when order matters, NPR. Now, order does not matter. We will divide it by the number of orders, and what we get is the number of combinations. This is often pronounced as n choose r. In how many ways? 3 things can be chosen out of 20 things. Can be written as 20 choose 3. That also equals 20 choose 3 equals to 20 factorial over 20 minus 3 factorial over 3 factorial. How many ways? 20 things can be chosen. 3 things can be chosen. 3 things can be chosen out of 20 things. 3 things can be chosen out of 20 things. Based on this idea, we are having this problem. The number of non-congruent integer-sided triangle whose sides belong to the set 10, 11, 12, 22 is, based on this idea. Based on the idea of triangle inequality and combinations. Three distinct cases will be here. One for scalene triangle, another for isosceles, another for equilateral triangle. Scalene, iso, equi. First, let us resolve this. Scalene triangle. The most important thing in solving this problem is triangle inequality, that is a plus b greater than c. So using triangle inequality, what are the scalene triangles which cannot be formed? We have 3 such triangles. (10, 11, 22), 10, 11, 21, using triangle inequality. That this is not satisfied. Then 10, 12, 22. These are the 3 triangles which will not satisfy us. Others will satisfy. So we just select Three sides.
Three sides.
We just select three sides. 13 choose 3. And subtract the three cases which cannot happen. So this will give us the case for scalene triangle. Now isosceles triangle. What are the isosceles triangle which are not possible? 10, 10, 20, 10, 10, 21, 10, 10, 22, 11, 11, 22. 4 cases are not possible. Now we just select two elements from the 13 to get the isosceles sides. Now why two elements? Suppose we just choose 22 and 19 as the two element. Now we just create our triangle with them. 22, 19, 19 is one triangle that we can form by the two elements chosen, and another is 19, 19, 22. So this will be multiplied by 2 because with the two elements we can form two triangles minus the 4 cases. Minus 4 cases. Now the last one, equilateral triangle. There is no kind of triangle inequality. Just simply 13 choose 1, which will give us 13. Now we need to find the value of this 13 choose 2, 13 choose 3, 13 choose 1. 13 choose 2 means choosing two elements out of the 13 element. We just say that if the two elements are 22 and 19, we can form, as I said, just choosing two elements. Then using the two elements we can have two isosceles triangles. So what is the value of 13 choose 3, 13 choose 2, 13 choose 1? You need to calculate. And you need to just add all these cases. The case of scalene triangle, add the case of scalene triangle plus isosceles triangle and equilateral triangle, you will get the answer. That's not my part. Proving 0 factorial equals to 1. Proving 0 factorial equals to 1. That's just a basic theory. In how many ways? You ask it yourself. We can select 0 things from n things. There is only one option, that we choose nothing. We can choose nothing. We can choose nothing. That is the only one option we are left with. We can choose nothing. So we are having one option, right? So n choose 0 equals to 1, or n factorial over n minus 0 factorial over 0 factorial equals to 1, or this is n factorial cancel, or we are getting 1 over 0 factorial equals to 1 over 1, or 0 factorial equals to 1. That is the funda. What are the problem solving strategy that we will proceed with? The most important thing, that we will not use the formula of permutation, we will use the formula of combinations. Then we will multiply it with the number of arrangements. First find the possible groups, ignoring the arrangements of elements inside the group. Then find the number of arrangements of this element inside the group and use the basic counting rules. Just product. Some other strategy, that often we memorize formula, but here we will not memorize any kind of formula because we are preparing for Ioqm. Since the Ioqm preparation cannot be accomplished by using formula because it tests our basics. First formula is, do not memorize formula. First funda. Break down into appropriate cases. Use basic counting rules. Useful problem solving strategy. Binary sequencing. Or you can use stars and bars. Okay, what is binary sequencing, stars and bars? I'll come to this. These are just symbolic. The first problem solving strategy that we have provided here, problem solving strategy. We will just show you application of the problem solving strategy here. We'll just show you application of the problem solving strategy here. How many different 3-digit number can be formed using the digit 1, 2, 3, 4, 5 such that the number does not begins with the smallest digit? First of all, let us choose 3 numbers. Then we will arrange them. We have 5, then 3. Now suppose the 3 numbers are A, B and C. It is obvious that this should be of the form without loss of generality. Without loss of generality. They should be like that. Greater than B, greater than C. Now one number is small. Now it is given that the smallest number, the number does not begins with the smallest digit. You can try to solve the question yourself also. It's better that you first try solving the problem. You can just pause the video. You can just pause the video because we are having a lot of problems to discuss at a single class. Because many are starting from scratch. So we should solve as more problem as possible. So it's better to pause the video. And it's recommended again and again. In all of our video, the system is to pause it, try solving it, and then looking at the solution, because simply looking at the solution will not help you. We should sit with a copy. So C is the smallest number. The number does not begin with the smallest digit. So the possible arrangements are, the number can start with A, then BC, or A, CB. It's not beginning with the smallest digit. Or it can start with B also. B is also not the smallest. BAC, BCA. So we are having 4 arrangements. Multiply by 4. That's why I am not using permutation. If somebody uses the formula 5 permutation 3, then this is wrong. This is the correct answer. This is the correct answer, guys. That's why. Now here we will use binary sequencing in this problem. An engineer is required to visit a factory for exactly 4 days during the first 15 days of every month, and it is mandatory that no 2 visit takes place on consecutive day. Then the number of all possible ways in which such visits to the factory can be made by the engineer during 1 to 15 June 2021. An engineer is required to visit a factory for exactly 4 days during the first 15 days of every month, and it is mandatory that no. Okay. Binary sequencing is that. Let the visit be denoted by 1. 1 means visit, he will visit. And 0 means he will not visit. He will not visit. So how many visits we are having? 1, 2, 3, 4. So how many 0 we will have? We will have 11 zeros, right? Let us place the 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, 11. In between the 11, these are the empty spaces. We are having 12 spaces where he can visit. If we just choose any 4 of the visit, we will see that none of the visit can be consecutive because at least 1 0 will be there in between 2 visits. We are choosing for the 1. So we just need to select now. We are having 12 and the visits are 4. 12 choose 4 and this is the answer. You just see such a simple concept came in JEE Advanced. This is beyond imagination. 12 factorial over 8 factorial 4 factorial 12 into 11 into 10. Am I doing it correctly? Yes. 9 over 24. 5. This is 45. This is 11. So the answer is 45 into 11. 45 into 11. 594. Okay. The answer is 495. 495. Answer. It was damn easy for us, isn't it? Now a question from Kvpy essay. Probably I have forgotten the year. That's why it's just simply written as Kvpy essay. How many ways are there to arrange the letters of the word education so that all the... Again the same thing we are applying. Vowels occur in the same order. Two consonants occur... The consonant also occur in the same order. No two consonants are next to each other. Consonant cannot be next to each other, so consonants are between the vowels. Vowels are E, U, A, I, O. Only one arrangement of vowels. 1, 2, 3, 4, 5, 6. In between the vowels, we will place the DCTN. So we are having 6 spaces, you can see, and 4 vowels. So the answer will be 6 factorial over choosing 4 spaces out of the 6 empty spaces. 4 factorial, 2 factorial. This will be 15. This is our answer. Because arrangements are also unique arrangement, UAI or DCTN. You just see how easily we are solving. Permutation with repetition. Most of you would have the idea of the formula, like n factorial over 7 factorial. Okay, n1 factorial and k1 factorial, k2 factorial. But here we will not use that formula. Because how this formula is coming? What is the logic behind that formula? First, we should search this logic. And that's why we will use our old principle. First choose, then permute. Try solving this problem. You can pause the video. You can solve it yourself. But look at our solution. Definitely you should not skip this solution. You should not skip the solution. Do not skip the solution. Very interesting thing is going to happen. Do not skip. Do not skip the solution. How many different flags we can make with 7 strips? If we have 2 white, 2 red, 3 green strips. How many different flags can we make with 7 strips? So we are having 7 strips here. 2, 2 and 3. One, 2, 3, 4, 5, 6, 7. First, let me think that where I will put the white strip. I can just choose any of the positions. Because 7 places are left, 7 choose 2. Now 2 positions have been captured by the white strips. For the red strips, we are left with 5 positions. 5 choose 2. And for the green strips, we are left with 3 positions. Then the formula comes. Okay, wait. 7 factorial, 5 factorial, 2 factorial over 5 factorial, 2 factorial, 3 factorial into 3 factorial, 3 factorial, 0 factorial. Now just see 5 factorial cancel, 3 factorial cancel. What we are left with? 7 factorial over 2 factorial, 2 factorial, 3 factorial. And I know that most of you who has been preparing for Ioqm definitely have seen the formula of permutation with repetition in their books. Yes, definitely we can apply the idea of basic counting principle. But I have derived the formula using the concept of combination. So that is also absolutely correct. And that's what I was saying, that not skip it. Because everything is interrelated. And here's the actual formula. Number of different permutation of n objects for there are n1 repeated items, n2 repeated items, and nk repeated item. Basically, direct question will not come. But while solving problems, you can apply this skill. You can apply your skill. While solving the problems, you have to apply this skill. Example I have shown here only. Application of problem solving strategy. First choose, then permute. How many flags can we make with 5 strips if we have 2 white, 2 red and 2 green strips? At the first glance you think that it's a problem of what? Sir, I guess it's a problem of, see, I am confused here. I am confused that it's a problem of, see, permutation with repetition. No, never. Try to solve it. Pause the video, try to solve it. This questions looks easy, but for many of the students this will be difficult. Consider that the stripes are either horizontal or vertical. You can just consider it. Now let's solve it. 2 white, 2 red, 3 green. Let us sort out into the cases that we have taken 2 white. We have taken 2 white, 2 red, 1 green, 2 white. Again 1 red, 2 green, 0 red, 3 green. All the cases of 2 white. How many cases we are getting from here? This is 5 permutation over 2 permutation. Sorry, what am I seeing? This is just, you simply find out 5 factorial over 2 factorial, repetition. Apply your logic, guys. Then it is 120 over 4. 30 possibilities. 120 by 4, 30. We are having 30 possibilities. Here also we are having 30 possibilities. 2 white, 0 red, 3 green. Here it is 120 divided by 2 divided by 6. Here only 10 possibilities. Add them all, you'd get 60, 70 possibilities. For the case with 2 white, then the case with 1 white, 2 red, 1 white, 2 red, 3 green, because this will be very well, yeah. 1 white, 2 red I am considering, and 3 green. Now can we consider 1 white, 1 red? We cannot. Or we can. Yes, we can. Because here it should be 2, right? Here it should be 2 green. Here it should be 3 green. Further we cannot consider. So how many possibilities? 5 factorial again over 2 factorial, 2 factorial. How many arrangements? First find the combination and then arrange them. And then arrange. 30 arrangements. 120 divided by 6. This is what? 5 factorial, repetition of 3 green, 3 factorial, 20. So here we have total of 50 cases. Now 0 white. Okay, last case. 0 white. 2 red, 3 green. 2 red, 3 green. Then this is what? 5 factorial over 3 factorial, 2 factorial. 5 into 4. 10 possibilities. So we'll add 70, 10, 50. 80. The answer is 130. Why? That also you are not understanding. 70. Add up the cases. 10, 50. 130. So is it clear? I hope it's clear. Some important formulas that one needs to memorize to solve the problems quickly. Among them, some formulas are written. I don't know who is writing these formulas. This you can say, this is important. This is very important. This is important. These other formulas are not important. Others are not important. Just I would say that others are not important. This formula is binomial theorem. Separate videos are coming, and this formula is also extended from binomial theorem only. One can easily prove it. So these three are only the important formulas. Let me hide the others. Otherwise, a lot of confusion will be created. This is a question from an old IITG question. I just tell you the approach. I did not tell you how to solve it. I just give you the hint. You can just first try it yourself. I am giving the hint. Just simply divide it and divide this. This is the basic concept. You will get two equations, then you can solve it. Then you can solve it. This is the basic hint. You solve it and then go for the next question. let's solve Ioqm question. Okay, that means that we have built our concept to solve the Ioqm problems even. I guess that I have added some more problems. What are these? Okay, 4 problems from Ioqm will be solving. That is PRMO. Whether I have completed all the charts or not. Okay. All the problems have been discussed. Very nice. Very nice. At least the ideas have been provided. You can first try it yourself, or most of you might have already solved it. So, there are 8 rooms on the first floor of a hotel with 4 rooms on either side of the corridor. This is the hotel. These are the rooms. This area is the corridor. Red carpet होता है ना, corridor. Red carpet, corridor. Then let us create the rooms. 4 rooms. These are the 4 rooms. Fine. 8 rooms. There are 8 rooms on the first floor of a hotel with 4 rooms on each side of the corridor, symmetrically situated. 4 guests must be accommodated in 4 of the 8 rooms. 4 of the 8 rooms, such that no 2 guests are in adjacent room or in opposite room. In how many ways the guest can be accommodated? Suppose the first guest is accommodated here. Then the second guest has to be accommodated in this room, because in symmetrically opposite or adjacent we cannot. Here we cannot. This is adjacent. This is symmetrically opposite. Similarly, this room will be accommodated. Again, this room will be accommodated. So we can see 4 persons are there. So in 4 factorial ways they will accommodate the rooms. For this room we are having 4 options. For this room we are having 3 options. Here we are having 2 options. Here we are having 1 options. 4 factorial. Now we just see the person can start from this room also. Then this room, then this room, then this room. So there are 2 arrangements again for selecting the rooms. This is for arranging the person and this is for selecting the rooms. 4 factorial is equals to 24 multiplied by 2. Answer is 48. Very easy PRMO question. This question is truly a beautiful question, where students will definitely give wrong answer because they will not study it. They will not study it. This is truly the beautiful question. There are 5 cities A, B, C, D, E on a certain island. Each city is connected to every island by road. In how many ways a person starting from A can come back to A after visiting some cities without visiting the city more than once and without taking the same road more than once? No. That is the most important thing. Where we will do the mistake? Okay, let me start with the mistake only. What are the cases that one can sort out? The logic is that he can visit all four cities, all four cities, four cities, three cities, two cities. Those will consider one city. Those will consider one city, they are wrong. Why? Because you just see, I'm starting from A. Suppose I have choose B. Then I'm going back to A. I'm using the same road more than once, isn't it? For this way, same road more than once. And here, most of us will be considering four cases, which will be extra. So most of the people will give the answer 4 more than the original answer. Most of you will give the answer 64, whether the original answer is 60. That is where the mistake is. Because going to A to B and then coming from B to A, you are using the same road. So now we are choosing two cities. And then we will arrange. 4 choose 2. 2 factorial. 4 choose 3. 3 factorial. 4 choose 4. 4 factorial. This is equals to 12. This is 24. This is also 24. Adding the all cases, we will get 60. Because this is extra. This we will not consider. That's why the question was special. There are several teacups in the kitchen. Some with handle, other without handle. The number of ways of selecting 2 cups without a handle and 3 cups with a handle is exactly 1200. Exactly 1200. What is the maximum number of possible cups? Some with handle, other without handle. The number of ways of selecting 2 cups without a handle and with a handle is exactly 1200. Try to solve it. So I am solving it. Let the total number of cups be x. Total number of cups be x. With handle, with the number of cups be y. So without handle, number of cup will be x minus y. Without handle, number of cups will be x minus y. We will select number of ways of selecting 2 cups without a handle. 2 cups without a handle. X minus y choose 2. 2 cups without a handle and 3 with a handle. 3 with a handle is exactly 1200. Three with the handle. This is x minus y. Considering x and y will make this a little bit messy. Let us forget the case and consider a new case. Let us forget the case and consider a new case. Then the number of cups with handle is x, without handle is y. Now this will be easy. So total number of cups will be x plus y. Now let us try. We have with handle x choose 3. without handle equals to 1200, or we have x into x minus 1 into x minus 2 into y minus 1 y minus 1 equals to 12 into 1200. Is it clear? Up to this it should be clear. Now x into x minus 1 x minus 2 y into y minus 1 equals to 2 into 2 squared into 3 2 squared into 3 into that's 12 into 12 into 100 2 square into 5 5 square. Now we need to find 3 consecutive numbers and 2 consecutive numbers from there. Five and 4, suppose this is 5, this is 4. 5 and 4. Five and 4 case is not possible because 5 and 4 we are left with a 5. For the 5 and 4 case we are left with a 5. 4 is gone, and then 16 and 9. This cannot be resolved into 3 consecutive numbers. I am not getting at least 3 consecutive numbers from here. Oh, 8, 9, 10. Yes, it's possible. This can be 9. Fine. This is 10 and this is 8. 8, 9, 10. This is possible. 10, 9, 8. So one possible value of x plus y that we are getting is 10 plus 5. Let us sort another pair. Let us sort out another pair. 5, 4, then 9, 10. Let's think. That is, y here now is 9. Y here is 10. This is 9. Now what are the possibilities? For 9 and 10 this is not possible. You just see why it's not possible. Because if we just take 10 from here, we are left with a 10. 3's factors are already taken out, and 16. For this part, x into x minus 1. So this, either we have to take 5 or 10. Any one value we have to take, yeah, for 5. So we are not getting any pair for 9 and 10. So this is rejected. This is rejected, guys. This 9 and 10 is rejected. Any other options in our mind? We have seen. Think for other cases also. We have to sort out all the cases, then only we can be assured that yes, no other case is possible. At least 3 or 2 cases will come. That's the gist of Ioqm. 25, 24. Okay. 25 is possible. 24 is also possible. Because we have so many 2's. 25 and 2 square. 2. We are having left with 2 whole to the power 3. 1 3 is also taken into 3. That is 8 into 3. How can we write it? Can we write it? 3, 4. Fine. 2. Okay, again a pair we have got. A new pair. That is x equals to 4 here. In this case, x equals to 4. So we have got the two cases. Another case we need to find. Another case we need to find. Another case we need to find. At least 3 or 4 cases will be there. Okay. Because this is a Ioqm question. This is a Ioqm question. It's PRMO question. So, and 2018 was indeed one of the difficult. Pattern was also changed a little bit. We have seen that this 5 is the main trouble created by 5 only. 16 is possible, 15 is possible. 15. So 16, 15. There we are left with 16. We are left with the 2 square. We are left with the 2 square and 5 and 3. This is what? 4 into 5 into 3. That is which can be written as 5 into 4 into 3. So we have got all the. This question is not yet solved. 5 into 4 into 3. All the 3 pairs have been sorted out. I do not guess that there are any other more possibility. 16 plus 5. 21. So the answer is 29 because 29 is the maximum possible value. Maximum. So the answer is 29 because 25 plus 4 equals to 29, which is the maximum value of x plus y. So it is solved. Maximum value we are getting is only from this pair. 25 plus 4. The maximum value we are getting from this pair 25 plus 4. Others, what you see? This is 21. What is happening? Yeah, perfect. This is 21 here. So the maximum value is 29. We can conclude from here that the answer is 29. This is again a easy question because it feels like easy and it's easy also. That n be the number of ways of distributing 8 chocolates of different brands among 3 children such that each child get at least 1 chocolate and no 2 child gets the same number of chocolate. This is the most important thing. Each child gets at least 1 chocolate. So we can, one possible distribution is 1 plus 2, 3, 5. Another is 1 plus 3, 4 plus 4. If we just try with 2 for the first child, then 2, 3 and 3. So we can see that only these are the 2 valid solutions and this is invalid. So let me just remove it. So the first case is this kind of distribution, 1 to 5 chocolates. Second case is 1, 3, 4 chocolate. So we have 8 chocolate for the first child. We are selecting only 1 chocolate. We are left with 7 chocolate. We are selecting 2 chocolate. We are left with 5 chocolate. We are selecting 5 of them. Now this 1 to 5, this is like that the first child is always getting 1 chocolate. This can be arranged in 3 factorial ways. Multiplied by 3 factorial. Similarly for this expression also. 8 choose 1. 7 choose 3. 4 choose 4 into 3 factorial. We need to just find it. This is 8 factorial. You can calculate it. One can calculate 2 factorial, 5 factorial multiplied by 3 factorial. This is 8 factorial, 3 factorial, 4 factorial multiplied by 3 factorial. 3 factorial cancels. 3 is only left. 8 factorial is common. 8 factorial is common. 3 over 5 factorial plus 4 factorial. 3 over 5 factorial plus 1 over 4 factorial. Just find it out yourself only. That would be better. That would be better. This is the calculation part. This is the calculation part. I just left it to you. I have shown you the process. I have shown you the method. You can calculate yourself because that's your part. No one is going to show you the method also. But I have shown you the method. I'm just re-explaining this how it is happening. This is the only way this can happen because each child should get at least one chocolate. This is the number of chocolates that children are getting. Okay. Now just think. Pointer is not there. Pointer. I guess pointer is not there. Okay. 1, 2 and 3. 1, 3 and 4. Then 1, 2, 5 and 3 factorial. Okay. 1, 2, 5 and 3 factorial. 1, 2, 5 and 3 factorial. Okay. Now this 1 to 5 can be arranged in 3 factorial ways. Is it so or not? 1, 2, 5. 2, 5, 1. So on 3 factorial ways are there. And distributing the first child, we're having 8 chocolates, selecting 1 chocolate, we're left with 7 chocolate, selecting 2 chocolate, we're left with 5 chocolate, selecting 5 chocolate. If you just multiply it, you will get this. Multiplied by this 3 factorial ways. This is the next case. This is also multiplied by 3 factorial. You'll get the ultimate answer. So all the questions we have covered that were past papers questions, and all the questions were beautiful questions. Whatever concept we learned, that choosing things, permuting things, arranging things, the strategy, this binary sequencing, how easily we are solving, or stars and bar method. So we have seen in all the questions that we need different knowledge. It's not like simple knowledge. We cannot solve anything with the simple knowledge, the simple formulas we cannot solve. We need to apply the skills, and that is the thing which is PRMO. That makes PRMO different from others. So we are in the end of our lecture. Thank you.